So the problem that your brain faces is this problem. Here's the world, sort of, right? And what happens is you take in a little piece of it here and a little piece of it here. So you get this little sample, and you get this little sample here. And your brain has to try and figure out from those samples what the real pattern is in the world. Good luck. That's a very, very hard problem, right? It's a very, very hard problem because this is usually not enough information to give you enough feedback on how well you're doing. When you may think, oh, well, don't I get correction? Like I bump into things and ow. Sure. The problem is that the correction problem is intermingled with this problem. This is called the projection problem. How do I get the big pattern from these little distorted and incomplete samples? Why is the correction problem? Because a lot of times the feedback you're getting from the environment isn't giving you that kind of clear, yes, no, like when I'm doing this. I'm not, it's not particularly pleasurable. I'm not suffering. Okay, but I still need to learn. Smooth might matter. I mean, doesn't smooth matter at some point in your life? Right? So, I mean, and that goes back to, again, simple associationism. It doesn't work as an explanation of learning within animal learning theory. So, you may think, well, what do we do? Like, how do we solve this? Now, we have an engineering solution to this, which is, it's a great engineering solution, and it's no help theoretically. So, when people make neural networks, these are artificial intelligence things that operate like brains, this is what they do. They give the network some of this input, and it has to try and come up with the pattern from which the input came. And then what you do is you take, right, what the real pattern is, it's called the target value. You take the produced pattern, what the network does, right, and you subtract that. This is highly simplified. I mean, Geoffrey Hinton would overwhelm you with way more math, okay? You get an error value, and then you take this error value and you use that to correct your neural network. And we use that, it's called back propagation of error, and it's a very powerful technique. It's great. It's how you can train neural networks to do voice recognition so you can talk on the phone to that annoying AI. What city, what town, all that sort of stuff, right? That's done this way. So it's a great engineering solution, and everybody knows that it works, but the problem is it's not a scientific answer. Because this way of teaching a neural network requires that the target value has already been learned by something. Do you understand why that's a problem? I can't have a theory of learning that requires for its functioning something else having successfully learned. Because then I can never explain how learning gets going in the first place. So you need what's called unsupervised learning. Now the way you get unsupervised learning, by the way, I'm going to get back to this weirdness, the synesthesia. Be patient, okay? Because it's cool. Well, I think it's cool. I know I'm a strange person, but okay. Here's the thing you do, right? It's a really interesting idea. I'm going to represent this as if it was two different networks. It doesn't have to be. It can be different sets of weights within the network, but it's sort of graphically easier to do that. And what you do is you have this part of the network, right, do that interaction. It's picking up little samples of data, and it's trying to come up with, it's trying to complete the pattern. It's trying to say, oh, I think the big pattern that this came from was this. And it's getting some feedback, pain and pleasure, and it's doing a really crappy job. Okay? So it comes up with some horrible model of the world, right? Some horrible, again, by model, I don't mean like necessarily representation. It comes up with some way of trying to complete the pattern. Okay? Now you may say, well, so let's label these, by the way, A and B. So what? Okay, well then you go to another phase and you switch. So now you stop caring about the world. Now this sounds bizarre, but you stop caring about the world. And please remember that I just said that. You stop caring about the world. So this thing has some very complex pattern it can generate inside of itself. And what it does is it will then do the following. It'll send little snippets, samples of its pattern to this part, right? And it basically says to this part, it says to B, can you figure out the big pattern that this little sample came from? Not the big pattern in the world, the big pattern inside me. Now notice what's going on here. The projection problem isn't being represented in the brain so much as this part of the brain is actually confronting it internally. So when myself and Tim Lilliclap and Blake Richards published a paper on this, part of this in 2009, we actually called it internalization because of that, because you're not representing the problem, you're actually internalizing it. The brain is not, like, this isn't standing for the world, it's standing in for the world. It's taking the role of the world. It's not right, representing the world in that sense. Now, you do this for a while, but there's a big difference. Because B can get something that A can't get. Because one of the things that A can give B is corrective feedback. It can say to B, hey, that was pretty good. You can do what's called a hill climbing heuristic. You don't need to know about that. It's, like warmer, colder. Hey, that was oh, crappy. Oh, better, warmer, colder, right? Until eventually B gets better and better at going from the samples to what the original pattern was. And you say, that's dumb. Because now you got two parts of the brain that are creating really crappy models of the world. What the hell good is that? Okay, well, here's what's good about it. Stop thinking about the world in that sense and think about the acquisition of a skill. Because the B network has started to acquire a skill for going from sample to original. It's gotten better at dealing with that distortion. It's developed the skill. And then we move to the next phase, right? Now, B can train A, because A is a crappy modeler, and B can say, you know what? Your modeling techniques aren't very good. This is distorting. This often doesn't work. Try this. Try this. I mean, I'm anthropomorphizing. You know your brain doesn't talk in English, right? Okay? So what B does is it trains A to be better at modeling. And then we go back to here, and we start the whole thing over again. So A is now a little bit better at modeling the world, makes a bit better model, and it goes through, right? And eventually, you get very good at predicting what the pattern is in the world. Now, you can have Cartesian worries about this. Well, can't this all be going on, and we don't really know what the pattern is, and maybe it's the matrix? Yes, I don't know. Who cares? Right? That's not what I'm talking about. I'm talking about how you actually function and whatever this is. If it's the matrix, and I can't possibly find out that it's a matrix, I don't really care. Okay? So, the thing is, what this does is without the brain ever having the target value, it can zero in on it. It can home in on it. Okay? Now, take a look at this. This is really cool because you've got two different things going on here. Right? This part of the system is, in a sense, learning or modeling. This part of the system is learning to learn or meta-modeling. It's modeling. It's not, learning is when you're paying attention to the patterns in the problem. Learning to learn is when you're paying attention to the patterns in your problem solving. And learning to learn makes you much more insightful. So this is also an insight generating machine. I want to tell you, and this is how Geoffrey Hinton is very playful, because he won't strike you as a playful person if you meet him. He's very staid and British and very dry accented, a lot of math, and it's kind of scary, right? But he's very playful in a lot of ways because he links these two together. He calls this wake and this part of the cycle sleep. Because the idea is, the joke, well, it's not so much a joke anymore, by the way, is this is what your brain's doing when you're awake, you're tracking the world, and what might you be doing when you're asleep that's like this, where you're inside this own bizarro, strange world where you're practicing skills? Yes, possibly dreaming. And there's more and more people who are investigating that dreams aren't so much encrypted codes from your unconscious as they are practice arenas for the acquisition of valuable skills. It helps to explain why animals dream. It's kind of hard to think that animals are dreaming because they're dealing with Oedipal issues about their mother and stuff like that. Okay. So this is really important. And I want you to also note that because it's modeling the world and it's also modeling itself. So it's inherently doing that bidirectional modeling we were talking about. Inherently. So this is also an affordance generating machine. So it can insightfully generate affordances because it's simultaneously modeling the system and modeling the world in this highly integrated fashion. Now it's turning out that the neuroscience is catching up to this. And this is happening in the last, I kid you not, in the last 4 or 5 years, because it's becoming, there's increasing evidence that the cerebellum is taking that role with respect to the cortex. Now, what do I mean by that? So remember what the A and the B were, right? Please. So, here's your cortex. It's linked up to the world in various ways. We'll come back to that in a sec. And then here's your cerebellum. Your cerebellum actually has more neurons than your cortex. It's a really powerful machine, but it's homogeneous, which means it's basically doing just sort of one thing that's sort of abstract and higher order. Now, we know that the cerebellum has to do with movement and bodily positioning and motor action, and that's really important. And think about that, how therefore gesture and movement can trigger the cerebellum. Okay? But there's a problem, and it has to do with the evolution of the cerebellum. It has actually expanded in evolutionary terms more than our frontal lobes. Now that's really hard to explain. It's not like, motor movement is becoming more and more hard for us. It looks like we've got a classic case of Darwinian exaptation going on here, that a machine that originally evolved for one design has been co-opted for doing other things. So this is the work of Ito and Van der Weert and some other names I'm going to throw at you very rapidly. But the idea is that, remember that internalization thing I just showed you? That's going on between the cortex and the cerebellum. The cortex is, learning, and the cerebellum is basically affording learning to learn. We already have empirical evidence to confirm that, by the way. If you lesion the cerebellum in rats, you can't destroy it, but if you lesion it, the rats don't lose learning, but they lose learning to learn. Okay? Now, but here's something that's more interesting if the cerebellum is doing this. Because, and this is one of the things that Van der Weert has talked about. Let's say, maybe if I actually separated it spatially, that would be good. So let's say I've got, this is, let's say, my working memory part of my cortex. This is my sensory motor. Maybe this is interoception. Interoception is my awareness of my inside of my body. It's like, that my stomach, right? That thing. Here, that's part of the visual cortex. Now, what's going on is you're getting what I call convergent internalization. The cerebellum is doing the internalization thing with this part of the cortex, also with this, also with this, also with this. Now, that's a really clever design, right? And I'm not arguing for intelligent design at all, because there's lots of stupid design in how you're laid out, right? Like you can die when you eat because of the way the larynx is set up. Okay, so I'm not, no crypto argument here. But what's going on here is, this is really clever because, right, it's like converging lines of evidence. Right? This internalization can be compared to that one, and you can say, oh, maybe they're saying the same thing. That's good, right? That adds plausibility. It helps the machine do even better at figuring out what the target value is, so that's a good design feature. But here's another really cool design feature. And now we're getting back to the synesthetics type stuff. The cerebellum seems to do something like this with the cortex. You're not doing very well, right? Well, let's do it this way. Working memory, you're not doing very well. The way you're trying to manipulate the information, not going well. Try this nice routine I've got with vision. Try that. And it swaps these internal models around. And Van der Weert explicitly argues that that's going to afford insight. And other people, Imeazu and Kawata in 2009, talk about the cerebellum internal model. An internal model isn't just that it's inside. Technically, an internal model is what I've been calling bidirectional modeling. An internal model is simultaneously trying to track the world and, right, what's going on in the body and the mind. It's doing that bidirectional modeling. So this is an insight generator, and again, it's an affordance generator.